correspondance. Je voulais. Comme ça, on n'a pas à refaire après.
Okay, perfect. So thank you very much for letting me presenting this this new theory, which we named entangled relativity. So as you'll see, it is not general relativity. The name has nothing to do a priori with quantum entanglement. So I won't speak about quantum entanglement today. The reason for this name, entangled relativity, stems from the fact that the theory cannot be even defined without matter. So in the etymological sense, matter and curvature are intertwined, they are entangled. So that's the reason of this for this name. So as we will see, it turns out that this specific theory is more parsimonious than general relativity. And general relativity is a limit of this theory. So this is what we'll see today. So first, I will recall some potential issues of general relativity, why we're looking for an alternative, a better alternative to general relativity. The first issue, I'm getting some feedback. Maybe someone didn't mute themselves. Anyway, one of the main issues, the singularities, the issue of singularities. As most of you may know, there's this theorem from Roger Penrose, which states that as soon as an event horizon forms, you will form a singularity, meaning that the laws of general relativity breaks down. And this is quite paradoxal because black holes are objects that are predicted by the theory. So the theory predicts its own issue in the sense that it predicts objects within which it cannot be defined everywhere. So that's kind of paradoxal. So that's one of the reasons to think that general relativity may have some issues. So the current consensus, though, is that most people believe that quantum gravity would solve this issue, the issue of singularity. Although most people, I think, believe that, not all people. For instance, Roger Penrose himself said recently that he no longer believed that quantum gravity could solve the singularity issue. But that's a minority view, I would say. Another issue is that spacetime might not have an operational meaning beyond the Planck scale, in the sense that you cannot have an experiment that probes scales beyond the Planck length and the Planck time, because in order to probe the scales, it would require an amount of energy that in such a tiny volume that you would form a black hole, according to the laws of general relativity. So it really seems that if there was not any operational meaning to the notion of space-time at the Planck scale. So more generally, so this is the path integral formulation of the core theory, meaning the laws of elementary physics as we currently know them. So this name core theory has been proposed by Frank Wilczek. And for those of you who are not familiar with this equation, it is it simply is the equation of all the elementary laws of nature that we currently know. So you have the standard model of particle physics here. You have gravity in the Ricci scalar. You have the coupling constant between the two, between Ricci and matter here. And what you can see is that in this equation, you have three elementary or fundamental dimensionful constants. You have Newton's constant G, you have the quantum of action Planck's constant h bar, and you have the causal structure constant C, also known as the speed of light. But from those three constants, you can build scales and or other constants, the constant of energy, a constant of mass, a constant of length, and a constant of Planck of time, and those are known as being the Planck constant. So the Planck energy is given here. You divide by c squared. You have the Planck mass, and you can do the same thing with the Planck time and the Planck length. Okay. So, but according to quantum field theory, the vacuum is not void. There are fields, it's permeated with fields, and those fields can fluctuate. And the energy of those fluctuations can be as high as possible, as long as the lifespan of those particles is inversely proportional to their energy, according to the uncertainty principle. But according to quantum field theory, there's no limits to the amount of energy that a fluctuating particle can have in principle. The issue is that when you consider general relativity at the same time, because in general relativity, there's a limit to the amount of energy that you can put in a given region, a given volume, before forming a black hole. And this limit here would be reached at the Planck scale, meaning that if you have a particle which has the Planck energy, then its scale would be the Planck scale, the Planck length, because the de Broglie length would be the Planck length. And therefore, you expect that for a particle with energy of the Planck energy, you would expect to have a black hole instead of a particle. Meaning that those fluctuations of particles should no longer be fluctuations of particle, but should be fluctuations of black hole or something like that. That's at least the naive picture, which led to this this idea of the quantum foam pioneered by John Wheeler some time ago. So even though that's probably a naive picture, that seems to be a picture at which we arrive when we merge quantum field theory to general relativity. But more generally, most programs of quantum gravity seems to lead to the same kind of idea, in the sense that the notion, the usual smooth and continuous structure of space-time seems to break down at the Planck's length and Planck time. So many quantum gravity programs lead to the understanding that space-time would be emergent from an underneath quantum structure that remains to be understood. So not all, I have to stress, not all quantum gravity programs do that. For instance, in asymptotic safety, when you reach the Planck length, the whole physics becomes scale invariant, and therefore you can still go at higher and higher energy, and the physics remains the same at all higher energy than the Planck energy, and the Planck and shorter distances than the Planck length. So not all programs propose that something. Well, all of them propose that something really transformative happens to the structure of space-time at the Planck length and the Planck time. Okay, and finally, I'll talk about another issue that has been debated a lot during the 20th century, but not so much during the 21st, I think, is that inertia can be defined from nothing in general relativity. And therefore, general relativity does not satisfy Mach's principle of Einstein, whereas it has built on this idea. So for those of you who are not familiar with Mach's principle, basically, so it's the third principle, fundamental principle of general relativity, as stated by Einstein himself. So this principle basically says that space-time, there's a consistent theory of relativity should not allow for a vacuum solution of space-time. And the reason is for metaphysical reasons. It has to do with the fact that for Einstein, a motion can only make sense if it is relative to something. You cannot even talk about defining a motion if there's nothing, because there's nothing with respect to define this motion. So for Einstein, it was really important to have this notion of relativity of inertia. This principle is also named the principle of relativity of inertia, in the sense that inertia exists only if there are things around. Okay. But the issue with relativistic theories is that as soon as you have a metric tensor, you have the inertial structure. And therefore, if your theory, relativistic theory, allows for a vacuum solution, then you can define inertia with respect to nothing. You can define a motion with respect to nothing, if not space-time itself. And therefore, space-time gets back an absolute nature that, that Einstein was trying to get rid of, kind of absolute nature à la Newton, I would say, that Einstein was trying to get rid of with his relativistic theory, hence the name relativity. So this principle was so important to him that when a journalist, during his first visit to the US in 1921, asked him what was really important with his theory of general relativity, he answered this. So it was formerly believed that if all material things disappeared out of the universe, time and space would be left. According to relativity theory, however, time and space disappear together with the things. So it really shows that it was really important for him that general relativity shouldn't have vacuum solution. But we all know that general relativity does. And actually, that's the real reason as to why Einstein introduced the cosmological constants. If you read the cosmological paper, his cosmological paper. Oh, there's a question. Yeah, sorry.
Yes, I would like to question. So, why is this really an issue with general relativity? Because I would not put this on the same footing as the two previous issues that you mentioned, the singularity issue and the quantification issue. Here, this is more a point of view, kind of philosophical principle. Yeah. It's not an issue for general relativity per se, I would say.
Not what. Well, it depends. Well, but you're right. Okay, you're right that this question has been debated a lot, and not everyone agrees whether it's an issue or not. And especially because the universe is filled with matter. So in the end, the problem does not to exist in our universe, given that we already have matter. So obviously, we don't have vacuum solutions. Nevertheless, I believe, but I would have to enter into much more details, that it remains an inconsistency of the theory. But yeah, I would have to take too much time in order to really debate that. What I want to go on and to stress is that this principle was the actual reason for introducing the cosmological constant. If you read the cosmological paper, the only reason for introducing the cosmological constant was to satisfy the principle of relativity of inertia. He had various arguments as to why his specific cosmological model would satisfy this principle, but this principle was really the motivation. And actually, so he was really upset when de Sitter found his solution of general relativity in vacuum with the cosmological constant, because he knew. So one of the reasons why he introduced the cosmological constant is because he knew that general relativity without a cosmological constant would have a trivial vacuum solution, the Minkowski, the flat spacetime solution. And for some reasons, he believed that introducing the cosmological constant would lead to the fact that general relativity wouldn't have any more a vacuum solution. And therefore he didn't like de Sitter solution, and he wrote that in a paper in response to de Sitter. If the de Sitter solution were valid everywhere, it will show that the introduction of the lambda term does not fulfill the purpose I intended, because in my opinion, the general theory of relativity is a satisfying system only if it shows that the physical quality of space are completely determined by matter alone. Therefore, no G mu nu field mode exists, that is, no space-time continuum is possible without matter that generates it. So, of course, we all know that de Sitter was right, and he finally he acknowledged the fact that de Sitter was right several years afterward, and since then he never talked about this principle anymore, because obviously it was not satisfied by general relativity. Okay, now I will introduce entangled relativity. I will talk about its formulation, and then a little bit about the phenomenology of the theory. So the formulation is simply you take the original linear coupling of general relativity between gravity and matter, and with this coupling constant here, and instead you assume, you make the hypothesis that you have a very specific nonlinear coupling instead. So it's a weird coupling. We'll see that. But the first thing to notice is that while you have one constant on the left-hand side here, a coupling constant, you no longer have a coupling constant on the right-hand side. So we'll see that in more details. But basically, that's the only thing. So all the ingredients are the same as in general relativity. You just assume that the coupling is not linear, but nonlinear. Okay, I have to stress that this theory, what I'll show, relies on a lot of work from many different people, and that it started with a work that we did with Aurélien S, which is currently at the LUTH Observatory. But back then, 10 years ago, we were pretty much at the same time at Caltech JPL. And we found out a decoupling that the decoupling that I will talk about, and that is used in this theory. So the theory has been published for the first time in Physics Letters B in 2015. But back then, we only knew that the theory would be viable for the solar system, and I was personally pretty sure that it would not for really dense objects such as neutron stars. I thought that the theory would not make sense, but I was wrong. And therefore, I started to believe that actually the theory is more interesting than I originally thought in 2015. And the theory was named only recently, like in the first paper with the name appeared in 2021. Okay, so that's the formulation of the theory. I show the path integral formulation rather than the action for a reason that will become obvious. So basically, it's because I want to define this this quantum of energy here. So this is the path integral. So you have this what is usually called the action here, except that it does not have the dimension of an action. It has the dimension of an energy squared. This integral here, and therefore, in order to have a quantum phase, you have to divide it by an energy, a constant of energy. So that's a quantum of energy squared here. Okay, a priori we don't know what it is, but it's a constant that is needed to define the theory. We'll see later on what it is. Actually, you can find what it is. Okay, the first thing interesting to notice is that this theory cannot even be defined without matter. Yeah, there's a question?
I had a question regarding the fact that you
I
have
don't hear you well. Can you get closer to the microphone, please?
I had a question regarding the fact that you have a scalar curvature in the denominator. So if you're in the midway, you're in flat spacetime, for instance.
Yeah, I'll get back to that afterward. That's one of the first question that people ask to me in general. So yeah, I will answer to that question. And if I don't, please raise your hand again. Okay, so Yeah, I was saying that the theory cannot even be defined without matter, in the sense that you need to have Lm in order to define the whole theory. Otherwise, the theory is not even defined. So, in that sense, it does not make sense to consider spacetime without considering matter fields at the same time, and that's the reason why we named the theory entangled relativity, because as matter and space-time curvature becomes intertwined. They cannot be separated. You cannot study them separately. You have to consider both at the same time, at the level of the very definition of the theory. Okay, so it seems that he solved this third issue, which was, as was pointed out, more philosophical. So it's interesting, but maybe not that much. Okay, so that's the path integral formulation. So in order to respond to the question, so indeed, that's one of the first question that people ask me when they see this equation, because so especially in the particle physics community, people would say, okay, but that's weird, because if I do particle physics, then I can assume that I neglect gravity, and therefore R is constant, if not zero, that would be worse. So R is constant, and therefore I have Lm squared, and this is obviously not standard physics, because standard physics would be Lm, here it would be Lm squared, and besides, whenever you have a square, you expect to have some theoretical issues, like the Ostrogradskian instability, the well-posedness of the Cauchy problem would not be, the Cauchy problem would not be well-posed, such kind of issues. So these comments are actually naive, sorry to say that, because the thing is that when you neglect gravity, you first have to know what gravity is. So this theory is not general relativity. So that means that you don't know what neglecting gravity means in this specific theory. And in order to figure out, you have to study the theory, the gravitational side of the theory, the classical gravitational side of the theory. So this is what we'll do now. So it turns out, and that's weird, but it's easy to prove, that there is an equivalence between this nonlinear action on the left-hand side and this action on the right-hand side involving an additional scalar field. This kind of theory is usually named an Einstein dilaton theory, in reference to the dilaton field in string theory, because you expect from string theories and in general from theories with more than 4 dimensions to have this kind of action here, with a scalar field that couples non-minimally to both the Ricci scalar and to matter fields here. So here you have this scalar field. Obviously, the equivalence only works if Lm is defined. If Lm is nothing, then here you don't have a theory, and here you get general relativity, which is not this theory. So the equivalence only works provided that Lm exists. Okay. Kappa, well, asymptotically, I would say at least is equal to the usual constant in general relativity, or at least that normalization that one will use, 8 pi g to c to the 4th. Okay, so the equivalence, the way to, the rigorous way to show the equivalence is to derive the whole field, the equations from the left-hand side and from the right-hand side, including the equations for matter fields, and to show that they are the same, okay? But it turns out that there's a really, really quick way to figure it out that they are the same. Because actually, so if you externalize the action with respect to the scalar field, then the solution is a constraint equation is given by this, this constraint equation here, kappa equal minus R over Lm. Now, just reinject that back into this action here, or into this, and you get back the action on the left-hand side. So that means that there are the same on shell, and therefore the classical level, they should be the same. But otherwise, of course, you can check that all the field equations are the same. Okay, so because of this, oh, and I forgot to say, because of this equivalence, the Cauchy problem is well posed, and actually, that's how the well posedness of F of R theories has been demonstrated, because for those of you who know F of R theories, they turn out to be equivalent to scalar tensor theories with potential. And thanks to this equivalence, then you can prove that the Cauchy problem is well posed. So for me, all along, it has been obvious that the Cauchy problem was well posed. But many referees disagreed. So I have to fight back a lot in order to have those publication published, because some of them were arguing that the Cauchy problem would not be well posed in this theory. So I'm not a mathematical physicist, so maybe I was missing something obvious, maybe. So I asked the question to two leading specialists in the subject. Okay, there's a question.
The question, yes, please. So what happens when the matter Lagrangian vanishes?
Yeah, I will go to that as well. Yeah, I will go to that point as well later on, or in the next slide, actually.
Because it could vanish pointwise, I mean, on some location.
What?
It could vanish, not in one space, of course, but in some location.
Yeah, of course, yeah, no problem. I will answer to that. Yeah. Okay, so the Cauchy problem is well posed. So ask to two leading specialists in mathematical physics, leading specialists in the Cauchy problem, Piotr Kruszal and Georgi Kijowski. And both of them told me that they don't see any reason why the Cauchy problem would not be well posed in this theory. And actually, there's a really quick and easy way to show it with assuming that matter field is a scalar field. Okay, so LM is let's assume that it's a scalar field. So you have now a scalar tensor theory with an additional scalar field. Well, you just have to do a conformal transformation, and the action that you get is general relativity with two scalar fields that are coupled to one to the other. And this is there's no problem with the Cauchy problem with these kinds of theories. So it's really easy to get the intuition as to why there wouldn't be a well-posed Cauchy problem in this theory. Okay, so that's the metric equation here, equation 10. So you see that it's slightly different from general relativity. You have this additional term on the right-hand side here. And much more puzzling, the stress energy tensor is not conserved here. And usually that's bad for a theory. When you have the non-conservation of the stress energy tensor, you expect the theory not to be viable because it would have been ruled out by observations. And for some reason that we will see, that's not the case here. So as usual for F of R theories, so here is not an F of R theory, it's more general than that. It's an F of R and LM theory, let's say. So, but as usual in F of R theories, you get, so they are equivalent to scalar tensor theories, and it turns out that you get the differential equation on the additional scalar degree of freedom by taking the trace of the metric field equation. So you take the trace of 10 with that, and you get the differential equation on the scalar degree of freedom here. Okay. Remember that the solution is such a kappa equal minus R over LM. Okay, and I will recall that in general relativity you have kappa equal minus R over T. Okay, so for the question that you asked and which is asked a lot, is that what happens when LM goes to 0? Because then it means that kappa blows up. Kappa blows up to infinity, and that's not correct for pretty much the same reason as to why kappa remains constant when T goes to 0 in general relativity, because R goes to 0 at the same rate, and therefore there's no issue. So the way to understand it is really important to keep in mind that this equation here is not independent from the other equations. Therefore, in order to understand what happens here when Lm goes to 0, you need to solve all the equations. And actually, you can have an intuition of what will happen when, at least when Lm goes to 0 and t goes to 0 together, when they both go to 0. Because obviously, this equation would not be sourced, would have 0, and therefore it is well-behaved. It's a well-behaved equation. So you should not expect anything special, anything difficult to happen when Lm goes to 0. So that's for the intuition, but you can verify that with an explicit exact solution. And this is what I'll show you now. So that's the charged black hole solution of the theory. It is given here. So it depends on the charge of the black hole, obviously. Oh, yeah, because in this theory, you cannot have black hole vacuum solutions. So you must have some form of matter. The easiest form of matter I can imagine is the electronegative field, a charge, and therefore a charged black hole. So this solution, when the charge goes to 0, has two limits. Either R minus goes to 0 and you recover the Schwarzschild metric. Okay, so the Schwarzschild metric is the limit of this black hole when the charge goes to 0. Or R plus goes to 0, and then you have a black hole with scalar hair. But we know there's a general theorem that shows that scalar hair in general are radiated away through gravitational waves, through monopolar gravitational wave during the collapse of an object. Therefore, you cannot form such a black hole with scalar hair. Meaning that the circle black hole in this theory should be, well, in astrophysical conditions, meaning not charged or not charged a lot, should be pretty much the Schwarzschild black hole. Okay, but the reason I showed this equation is because, well, obviously, if the charge goes to 0, Lm goes to 0. But you have to remember that the Ricci, the spacetime metric, has been created by this matter. So it depends also on the charge, in a way that the ratio between the two is perfectly well defined when Lm goes to 0. Okay, so that's an example that shows that it's not that because Lm goes to 0 that there's an issue. You have to solve the whole equations. And actually, the equation that you solve are well behaved even when Lm goes to 0. So you shouldn't expect anything difficult to happen here. It's not a general proof, obviously. So if there are mathematical physicists in the room, that could be something to check. But I think there's really no reason to expect anything difficult here. Okay, because of this scalar tensor form, you can do a conformal transformation of the spacetime metric, as is often do. And then if you do that and you assume that you only have an electronegative field, you recover a usual Einstein-Maxwell dilatant theory here, okay? Where alpha here takes a different value for each kind of theory. Okay, so for this specific theory, for entangled relativity, alpha equal 1/2 square root of 3. But for a bosonic string theory, alpha would be equal to 1. And for a 5-dimensional Kaluza-Klein theory with one dimension being compactified, you would have alpha equals square root of 3. Okay, so different values of alpha correspond to different theories. But for whoever has been working on this kind of theories, know that they are highly constrained by observations. Usually they are constrained in a way that alpha has to be close to 0 for the theory to pass all the tests that we know. So the question is, why do I still believe that the theory is viable? It is because it is at a really, really specific point in the theory space that leads to an exact cancellation in the field equations. Okay, we call that an intrinsic decoupling with Aurélien S. Some 10 years ago, we found this decoupling in a different framework, but this is how it works. So basically, you have this equation here on the additional scalar degree of freedom. you can see that whenever the on-shell matter Lagrangian, so what is the on-shell matter Lagrangian? Is basically the Lagrangian when you inject back the actual solution of the field equations. So for instance, for electromagnetism, the Lagrangian is proportional to f squared, f being the Faraday tensor, okay? But on shell, for a purely magnetic field, for instance, it would be proportional to b squared, whereas for a purely electric field, it would be proportional to e squared. And for radiation, it would be equal to 0 on shell, okay? Lm equals 0 on shell. So that's the Lagrangian, and when you inject back the field solution. So you can see that whenever Lm on shell is equal to the trace of the stress energy tensor, then the scalar field is not sourced. Okay, and if it's not sourced, then kappa being constant is solution. And obviously for this solution, what you get is that this is equal to 0, and therefore this is general relativity, and this is equal to 0, therefore you get back the conservation of the stress energy tensor, meaning that you get back the general relativity minimally coupled to matter. So now the question is, when does that happen? When do we have Lm is equal to T? Well, that would happen, for instance, for a universe entirely made of dust with null radiation, with electromagnetic radiation. Because for dust, the Lagrangian is just the sum of the masses times c squared, okay? Whereas for electromagnetic radiation, the on-shell Lagrangian is equal to 0, okay? And the trace of electromagnetism is also equal to 0 because electromagnetism is a conformally invariant theory. Okay, that means that for a universe entirely made of dust with null radiation, you don't expect the theory to deviate from general relativity, or at least you shouldn't deviate much. But that's a good thing, because our own universe, as we can see it today, is really well approximated as being made of dust with null radiation. So that gives an intuition as to why the theory, or at the qualitative level at least, as to why the theory should not be much different from general relativity for our universe, or for a universe like ours, like a universe that we currently see. Okay, so that's at the qualitative level. But at the quantitative level, we did several studies. There are many things that remain to be done, because it's a fairly recent theory. Yes, there's a question.
Since you're making the connection with the physical universe. Since you're making the connection with the physical universe,
yes,
where does the cosmological constant would appear in this theory?
That's a good question. That's an excellent question. So I will mention it really slightly now, and otherwise I have backup slides. So I'll mention it, and please ask your question again at the end, because I have backup slides on that. But that's a good question, and I will answer right away about at least part of the question. So what we can see is that for a universe made of dust and electromagnetic radiation, the scalar degree of freedom freezes because of the expansion. Basically, you have a friction term in the scalar field equation, and therefore the scalar field just freezes where it was, irrespectively of the previous dynamics of the scalar field. And therefore, you get back general relativity at the cosmological level. But you get back general relativity without a cosmological constant. And that's indeed something really important to stress. And it is not allowed to put a cosmological constant by hand in this framework. Because if you do that, then you would have a prediction that the constant G varies with time, and we have high constraint on the variation of G. So you cannot have this simple solution of adding a cosmological constant by hand. And more broadly, in general, it would be much difficult to have a dark energy candidate that allow for the acceleration of the expansion of the universe without at the same time generating a variation of G. So in that sense, it's a really much more rigid framework than in general relativity, where you can invent an infinite set of models that act as a dark energy. Here, that won't be the case. Your your dark energy models will have to be really specific in order to be able to explain the acceleration of the expansion of the universe. But the first thing is that you cannot simply add by hand cosmological constant here. What we found also is that neutron stars are at max a few percent more massive than the ones of general relativity, and I was really not expecting that. And I recall that all of this is without any theoretical parameter that can be adjusted. We have no free parameter in the theory, so that's really important to stress. So the exterior spherical black holes cannot be distinguished from the ones of general relativity in astrophysical conditions. At least we've shown that for spherical black holes. Now we have also shown that for rotating black holes with a slow rotation, and it remains to be done for general rotating black holes. And because of this equivalence with the Einstein-Maxwell-Dilaton theories, we can use previous work in the literature for gravitational waves that have shown either analytically or with computers that the gravitational waves emitted from the fusion of black holes wouldn't be different from the ones of general relativity as long as the charge of the two black holes merging is not very different, significantly different. And because we're working with astrophysical black holes, we don't expect both of them to be charged or charged a lot, and therefore we expect to have the same gravitational waves as general relativity for the merging of black holes. It could be different for neutron stars, but everything remains to be studied in this framework within this theory. Okay, so the broad consequence of the decoupling is that the ratio between R and Lm, that has been called kappa, varies much less than the spacetime metric. That's not always the case, but that would be the case for a universe that looks like ours. Okay, so basically, you quite generically, you have that this nonlinear weird equation that we started with can be written in this form that is much more usual. And if kappa varies much less than the metric, it means that in many situations, you can just neglect its variation. That would be the case, for instance, in the solar system. Its variation of the solar system is way too small to be probed by any current experiment or observation. And therefore, you can just take it out of the integral and you recover the general relativity, the action of general relativity, meaning that general relativity is a limit of the theory, and it's a predicted limit. It's predicted by this intrinsic decoupling that I talked about. Okay, but now let's come back to the path integral formulation. So usually standard quantum field theory on flat spacetime, what it is actually, well, flat spacetime as our current understanding of physics says that a flat spacetime does not exist in nature. It's just a useful approximation on scales where you can neglect gravity. But otherwise, observation seems to indicate that a flat spacetime does not exist in nature, just a useful approximation. So when we talk about standard quantum field theory on flat spacetime, what do we mean actually is that quantum field theory when gravity is neglected, when the gradient of the metric tensor is neglected. So to the original question that was, what does it mean in this theory to neglect gravity? It means that you neglect the variation of the metric, but you can also neglect the variation of the ratio between R and Lm. And I remind you that in general relativity, R over T is a constant also. So that means that when you do a standard quantum field theory, meaning that you neglect gravity, what you can do is that you just neglect all the gravitational fields here. So you take kappa out of the integral and G, you don't consider it anymore. So now that gives a way to identify what was the quantum of energy epsilon. Because if you want your theory to get a standard quantum field theory back in this limit, then you have to identify the two. Okay, so if you do the identification, what you find out is that this energy constant has to be the Planck energy. Okay, so now you know the only parameter of the theory, it has to be the Planck energy in order to recover standard quantum field theory. So it's a bit like in general relativity, you have this coupling constant kappa, and the value of kappa is given by the fact that you need general relativity to give the theory of Newton back at the Newtonian level. And this is how you determine kappa to be equal to 8 pi g to c to the fourth. That would be the same thing here. Because you want the theory to give back standard quantum field theory, then you must have that epsilon has to be the Planck energy. I say the Planck energy, it's actually the reduced Planck energy. Okay. Sorry, there are people drilling in my building. I hope you don't hear. It's not too loud on your side. It's a bit loud on mine. Anyways, when gravity is neglect, yeah, there's a question. Yeah.
Yes, please. So when you say G is considered to be constant in the first block, what do you mean exactly by this? Because as I understand, you cannot have Minkowski as an exact solution in your theory. So what do you mean by a metric being constant?
But Minkowski in this. No problem. So you have the same property of the space-time in the theory at local scale. If you remain at a given specific scale, you can always assume that that your metric is flat on this scale. So it doesn't change anything with this respect. Locally, your space-time still looks Minkowskian if you are at the right scale. So no issue with that.
Thank you.
Okay, so what we found is that standard quantum field theory is a specific limit of the theory where the variation of kappa and g can be neglected. And the only parameter of the theory turns out to be the Planck energy. Another thing that I think it's really interesting is that, okay, in this equation, during the identification, in this equation, you have exactly two constants, one on the right-hand side and one on the left-hand side. The constant on the right-hand side is epsilon squared, and the constant on the left-hand side is c. Kappa is not a constant, it's a field, and therefore h bar is not a constant either. And that was kind of obvious from the beginning because the quantum of action never appeared in the formulation of the theory. So you would expect it to be not elementary, but emergent. And the really interesting thing is that because of this identification, you can show that h bar actually is proportional to Newton's constant. So even though if at the scale of particle physics, where you can neglect gravity, h bar will be constant, it can change a little bit over very big distances where gravity cannot be neglected. And I will give some specific numbers as to how much it can vary in the next slide. But the thing is that in this theory, h bar is proportional to g. So it seems to indicate a direct link, direct connection between the quantum world and the gravitational world. And moreover, it means that in this theory, the weak gravity limit, meaning that when g goes to 0, is also the classical limit when h bar goes to 0. For whatever reason g is small for whatever reason g is small, it would be the same reason as to why h bar is small in this framework. So I believe that's also is something pretty interesting to keep in mind. Okay, now regarding the orders of magnitude of this variation, the variation of h bar. So that's a simulation for a neutron star, assuming a specific equation of state, of course. And so on this curve here shows the variation of a normalized version of h bar, let's say, or maybe 1 over h bar, I don't remember, something like that, but that's a normalization. At infinity, it reaches 1. Okay, and you can see its variation here. The vertical line is the radius of the neutron star, and you can see that the value of h bar between the surface and a remote observer varies by less than 1%. So that's the order of magnitude that we expect from this theory, and that's for the densest objects in the universe that are not hidden behind a horizon. So that's the scale of the highest variation of h bar that we can expect in the observable universe from this theory. So it's not a lot, a few percent, less than a few percent. Okay, that's for one simulation, but here is represented 4,000 simulations for various values of the central densities. The central density. Here you have general relativity in order to show the comparison with general relativity, and above you have the results with integral relativity. So basically, you have each simulation will give you, for instance, that the neutron star should have a radius of 16 kilometers and should have a mass of 1.25, say, or 1.3 solar mass. So that's what gives you the simulation. First thing that you can notice is that the neutron stars without free parameter, I insist, without free theoretical parameter. There are assumptions, of course, that you need to make, but otherwise you don't have any free theoretical parameter to adjust. So without any free parameter to adjust, the first thing we can notice is that neutron stars are always more massive than in general relativity in this theory. Not a lot, but always more massive. It can be up to, I think, 8% or 6%, depending on the way you define the mass, whether it's the ADM mass or the mass at the radius, whatever. So it's not a lot. And you can see the scale of the variation of h bar between the surface of the neutron star and a remote observer. You can see for the densest neutron stars, it would be up to 1.4 or 1.5% at max. Okay, so that gives you, and the scale of the variation is through several kilometers, meaning that for particle physics phenomenon, for instance, that happens at the surface of the neutron star, like what lead to the emission of X-ray, then it would be insensitive for this phenomenon. The h bar is perfectly constant. Okay. So that's the path integral formulation. I recall the path integral formulation of quantum general relativity. With you can see the appearance of this Planck length squared, which indicates that the Planck length has something really important to do with the theory. Yes, there's a question.
Yes. So when in the previous slide, when you showed your solutions for neutron stars, you solve for your field equations with this kappa, which is proportional to the Planck, which is not a Planck constant, which is not constant. It's a field. But so in the physics of the neutron star, you have quantum physics, and I was wondering if you included this varying Planck constant in the quantum physics that appears in the matter of the neutron star.
No, that's an excellent question. I haven't done that because for now it's too complicated, I would say, but that's something really interesting to look at. So what we did is a kind of exploratory study. So we just assume a specific equation of states. But you're right, if h bar changes within the neutron star, it should change physics, meaning that the usual equation of states that we consider for neutron star should be slightly modified. But you can see that the amount of modification of h bar is pretty small. It's a few percent. So you expect to have a modification of the laws of physics, of nuclear physics at the few percent level. But eventually, yes, this is something that will have to be taken into account indeed. In the sense that you will have to see what is the back reaction somehow of this change of h bar onto nuclear physics. But this is tough to figure out. So I haven't done that, obviously, well, for obvious reasons. Yeah.
Maybe this is not so tough if you consider the original Oppenheimer-Volkoff equation state, which is not physical because it completely neglects a strong interaction between the nuclei. So you take a free Fermi gas of neutron. This is what Oppenheimer-Volkoff did actually. So here you see the explicit dependence in h bar, and you can compute everything with this. It's quite simple actually to do with this. It's not astrophysically relevant, but if you want to see the effect, go back to the original Oppenheimer-Markov work. Then you have an equation of state where you have an explicit dependence in H bar because this is simply a free Fermi gas.
Yeah, thank you for pointing that out. That's really interesting because, especially because I'm currently thinking, and actually there's the intern that will do that online, working on the white dwarf. And therefore, this will be perfectly relevant for white dwarfs, I believe. And therefore, your comment is really, really interesting. We will try to indeed consider that.
You will get a maximum mass which is around 0.7 solar mass, which is not realistic because, of course, in doing so, you completely neglect the strong interaction. But just to see the effect on the variation of H bar.
Yeah, but I note your idea to consider a Fermi gas and to study that. If you don't mind, please, could you send me an email with more details, such that I'm sure that I didn't, because I took some notes, but to be sure that I didn't miss anything, that would be too bad, I think. But thank you for, that's an excellent comment. Okay, so there are only two universal constants in the definition of the theory, the causal structure constancy and the Planck energy. So that means because you only have two elementary dimensionful constants in the theory, you no longer have enough constants in order to define a Planck length and a Planck time in the theory. And therefore, you should not have any reason to expect anything special to happen to the structure of space-time at the Planck length and the Planck time. Or say otherwise, you shouldn't expect the difficulties of quantum general relativity at the Planck scale. That does not mean that the theory wouldn't have other difficulties, other problems, other issues, either before the Planck scale or afterward, but at least it's not even something that exists in the theory, the Planck length and the Planck time. So you shouldn't expect anything special there. Okay, so I would argue, of course, that this is circumstantial evidence that space-time may be actually elementary to any scale. That's a circumstantial evidence, and it will take a lot of work in order to really figure out. Now, the issues of singularities. So in the definition of the theory, you can see that kappa negative is not prohibited per se, meaning G negative is not prohibited in the theory. Okay, we've seen that in our universe, the biggest variation that we can observe is a few percent variation of G. So we shouldn't observe in our universe, G is always positive and it varies a few percent. But we can imagine that at even higher densities, such as inside black holes or in the primordial universe, maybe it is possible that kappa becomes negative. I say maybe because there's no, even though it's not prohibited that kappa is negative, maybe the field equations are such that it is not allowed to go from kappa positive to kappa negative. Maybe if you start from initial conditions where you set kappa to be negative, then you remain kappa negative. And when you start with your initial conditions such that kappa is positive, you remain in with a universe with kappa positive. This has to be studied at the mathematical level, whether it is possible to have a transition from kappa positive to kappa negative. But that's a priori a possibility that has to be studied. Unfortunately, the issue with this theory generally, the reason why it's somehow more difficult to study it, is that you need matter in order to you need well-defined matter in order to make those studies, and therefore if you are too naive with the matter field that you consider, well, the answer that you'll get is too naive as well. So yeah, so that's a possibility. So maybe this way, maybe from other reasons, it will be able to solve the issue of singularities, whether in for black holes or in the primordial universe. Okay, so that's a wrap up. So this theory is a simple reformulation of the general theory of relativity, which turns out to reduce the number of universal constants, and usually it's something that we like. It turns out that it recovers general relativity and the standard quantum field theory in a generic limit, which look in a limit that correspond to our current universe. It has no elementary length or time scales and has no free parameter at all. And therefore it seems to indicate that space-time might not be doomed, as several famous people have been arguing in the last decades. So I would say that it's an entirely new direction to explore and to evaluate without anything exotic. That's really something important. You have no extra dimension or things like that. And it makes a really clear new prediction that H bar can vary depending on gravitational phenomena and without free parameter. So if we can, well, we can probably, if we can see that, then it would be a smoking gun in favor of this theory. Sorry. Yes, there's a quick. I'm done with the presentation. I have a lot of backup slides to answer to other questions. But yeah, there's already a question. So please get closer to the microphone because it's somewhat difficult for me to get what you're saying. Thank you.
Yeah, one question, please. So regarding the first point on that concluding slide, so can you repeat the argument to say that you don't have an elementary time length? Because, for instance, you have an elementary energy. You have this energy quantum with epsilon, which appears in the theory. So now, if you consider the Heisenberg uncertainties relation, then you will get naturally associated to energy time scale, no? If you assume some limiting value of a Planck constant.
So I'm not entirely sure I got your argument. Because
I mean, if you consider
well, from the Heisenberg principle, of course, you can somehow transpose energy to a time. Is that what you're saying?
My point. Yes, exactly.
Yes, but that's really interesting because it leads to another question: is that if H bar varies, then you cannot do the canonical quantization anymore, because the canonical quantization assumes that H bar is constant. And therefore, you have to do everything through the path integral instead, meaning that probably, I'm not sure about that, but I think so, you lose the equivalence between the canonical quantization and the path integral. And the canonical quantization is only valid when H bar is constant. And therefore, it also probably means, but this has to be studied in details, that the Heisenberg principle gets modified in this theory. But I haven't done that, so this is an open question.
Thank you.
Question, please. Sorry to annoy you, but I want to go back to the question of the cosmological constant because it seems like there's one in the universe.
Yeah, that's a important question. Okay. Okay, so if you assume a flat Friedmann-Lemaitre-Robertson-Walker metric, then you can show that the scalar field goes to constant, freezes really quickly at least as soon as you enter in the matter era, because in the matter era is dominated by dust with electromagnetic radiation. And therefore, what you have is that you have this equation for the scalar field, the normalized version of the scalar field, and this is a friction term. If H is positive, that's a friction term, and therefore the scalar field freezes very quickly. Okay, so now what you need to have the acceleration of the expansion of the universe, you can have a cosmological constant. That's not an option in this theory. Why? Because if you have a cosmological constant, then you would have a source for the scalar field, and G is proportional to this scalar field, or the inverse, I don't remember, meaning that you would have a variation of G over the cosmological time, and we have severe constraint on the variation of G on cosmological time. So you can imagine that you have a dark energy model instead, but the issue is that if your dark energy model is such that it is not equal to the trace of the stress energy tensor, then you have no decoupling again, and you have this variation of G over cosmological time. So you know that those two options are not options in this framework. The only option that you have is that whatever dark energy is, it has to be proportional to the stress of the stress energy tensor. So there could be different models that do that. I proposed actually that the solution that has been proposed for general relativity for the value of the cosmological constant is could be used here. And this potential solution is that dark energy is related to the quantum trace anomaly of QCD in curved spacetime. So that's a possibility, maybe not the correct one. But in any case, I would say that this problem of cosmological constant is probably related anyway to the UV of the theory, to what happens on spacetime at really the fluctuation of spacetime at a really high energy. Because in general relativity, this is where you have the issue. Because if you use a cutoff the Planck scale, when obviously your spacetime should be much more curved than what we see in observationally. So there's an issue here anyway. So I believe that this issue of the dark energy, whether in this theory or in general relativity, would only be really understood if you really understood the UV of the theory. But that's a belief. Maybe I'm wrong about that. But yeah, so in the end, there's no clear solution for the acceleration of the expansion of the universe for this theory. So it's an open question.
Question, please. Thanks a lot for the nice talk. For me, it's a very basic question. I mean, I don't know if it's basic, but from the very beginning. So, like you said, that this theory is a kind of f of the which is scalar on the matter Lagrangian. I mean, f of r on LM theory seems like a particular case. But something among all the possible theory of this type. So this one seems to have nice properties, but why? I mean, there might be other ones. So why? I mean, only this one. I mean, is it possible to find other one which behave well?
So I cannot answer whether there exist others, but this is a possibility indeed. But I will answer why. So basically, whenever you have this nonlinear coupling, it means that you will have a scalar degree of freedom that couples to matter, and therefore, in general, you will have something that is deviates a lot from observations. And the reason why this theory turns out to work out well is because of this intrinsic decoupling, this exact cancellation in the field equation. And to have this exact cancellation, you need to have this really specific form. That does not mean that there are not other forms that exist that would have the same property, but I don't know any other.
Okay.
And it's actually really hard when we found this action by accident. It's really serendipity, I would say. And it turns out when you play with nonlinear action like that, you see that it's really hard to have something that makes sense in the end.
Question, please.
Hi, Olivier. Thank you for the talk again. I was just wondering, would you suggest any particular test for this theory, like something that would be quite specific to the theory?
Yeah, well, the variation of h bar is one of these tests. So for neutron stars, I'm not quite sure because I don't think we can probe physics. So the idea that I would have is that for white dwarf, if we can have a precise spectrum at the surface of a white dwarf, maybe it would be possible to check the variation of h bar, because the variation of h bar should imply different spectrum, because obviously the emission spectrum is different if h bar varies. So for white dwarf, the variation of h bar should be smaller, but maybe the spectra that we have from white dwarf would be more precise than for neutron stars, because I think for neutron stars we only see X-rays, and I don't think that we can know the spectrum of X-rays with great accuracy. So that's one possible test. It turns out that last summer I worked on the correction to the Shapiro delay in the solar system, and it's C⁻⁴ effect, meaning that it's a next to leading order effect, but it's not that far from what we will be able to check with the more experiments on Bepi-Colombo, the spacecraft Bepi-Colombo. So maybe in a foreseeable future, it would be able to test the prediction on the correction to the Shapiro delay in the solar system. And there might be others that I don't remember, but yeah, that's the main that I have in mind right now. But I would say that really the fact that h bar varies would be clearly the first thing that I will try to test with this theory.
Thank you. Question? Question from Zoom? Thank you very much, Olivier, for a nice talk.
Thank you.
Thank you.
Thank you, everyone. Thank you, everyone. My apologies for not being here with you today. I'm trying to reduce my carbon footprint, and it's really a pain in the ass to come to Paris by train. It's really long from Nice. But I would have loved to be here with you, and I hope that I will have the occasion to come sometimes. Please do not hesitate to contact me if you have any question or whatever. No worries, please don't hesitate. Thank you all for attending, and I hope to talk to you at some point. Bye.
Bye.